Understanding multiple linear regression, MLR. Multiple linear regression, MLR, is a vital statistical technique employed extensively across various fields, particularly in econometrics and financial analysis. This powerful method utilizes multiple explanatory variables to forecast the outcome of a response variable. Unlike simple linear regression, which evaluates relationships based on a single independent variable, MLR delves deeper by incorporating several independent variables to construct more sophisticated predictive models. Key takeaways. Definition: MLR is a statistical technique that uses several explanatory variables to predict the outcome of a response variable, making it more versatile than simple regression. Applications: MLR finds applications in diverse areas, including econometrics, finance, medicine, and social sciences. Forecasting and relationship explanation: MLR is capable of providing forecasts, elucidating relationships between financial variables, and testing existing theories. Formula and calculation of multiple linear regression, MLR. The mathematical representation of MLR can be succinctly expressed as follows. Y_i equals \beta_0 plus \beta_1x_ I1 plus \beta_2x_ I2 plus \beta_px_ IP plus \epsilon. Where y_i equals dependent variable, the outcome we are trying to predict. \x_ij equals explanatory variables, independent variables. \beta_0 equals y-intercept, constant term. \beta_j equals slope coefficients for each explanatory variable. \epsilon equals error term, residuals, representing the difference between the actual and predicted outcomes. This equation forms the backbone of the MLR model, enabling analysts to gauge how varying independent variables will influence the dependent variable. What multiple linear regression, MLR, can tell you. MLR provides analysts with a framework to understand and predict how changes in independent variables can impact a dependent variable. The effectiveness of this model hinges on several key assumptions. 1. Linear relationships. It is essential that a linear relationship exists between the dependent and independent variables. 2. No multicollinearity. The independent variables should not exhibit perfect multicollinearity, i.e., they should not be too highly correlated with each other. 3. Independence of observations. Data points should be selected independently and randomly. 4. Normality of residuals. The residuals should be normally distributed with a mean of 0 and a constant variance. The coefficient of determination, R². In MLR, one common metric used is the coefficient of determination, \R², which quantifies the proportion of variance in the dependent variable that can be explained by the independent variables. However, while \R², will always increase with the addition of more predictors, it does not inherently indicate the quality or relevance of those predictors, making it necessary to evaluate additional criteria when selecting variables. Example of how to use multiple linear regression, MLR. Imagine an analyst investigating how market fluctuations affect the stock price of ExxonMobil, XOM. In this scenario, various factors could influence the price, including market indexes, such as the S&P 500. Commodity prices, like crude oil prices. Interest rates, economic conditions often reflected through interest rate changes. The MLR model would leverage these factors to develop a linear equation predicting XOM's stock price. For instance, with respect to the model, \y_i equals price of ExxonMobil. \x_I1 equals interest rates. X underscore I2 equals oil prices. X underscore I3 equals S&P 500 index value. X underscore I4 equals price of oil futures. The difference between linear and multiple regression. The core distinction between linear regression and multiple regression lies in the number of independent variables analyzed. While ordinary least squares, OLS, regression focuses on one independent variable's impact on a dependent variable, MLR accommodates analyses involving multiple independent variables. Benefits of multiple regression. 1. Comprehensive modeling. MLR empowers analysts to construct models that accommodate various influences on an outcome, exceeding the limitations of simple linear regression. 2. Increased predictive power. By factoring in more variables, the accuracy and reliability of predictions are enhanced. Practical considerations for implementing MLR. While the complexities of MLR can be daunting, especially with larger datasets and numerous variables, statistical software such as R, Python, or even Excel can facilitate the computation of multiple regression analyses efficiently. Is multiple regression always perfect? Despite MLR's robust capabilities, it is essential to understand that models may not always create perfectly accurate predictions, as individual observations may vary slightly from the expected outcomes due to inherent data noise. Hence, residual analysis plays a crucial role in evaluating model fit. Conclusion. Multiple linear regression, MLR, serves as an indispensable tool for analyzing and predicting the relationships between variables. Its ability to accommodate various explanatory factors provides insight and depth that is often necessary for informed decision-making across fields ranging from finance to healthcare. By leveraging MLR, analysts can navigate complex datasets, uncovering valuable patterns and forecasts that enhance strategic planning and operational insight. Whether evaluating stock prices, assessing market trends, or conducting academic research, MLR remains a foundational method for robust statistical analysis.